My name is Sam Gisi, and I am a student at North Dakota State University. And today, I'm going to talk to you guys about a specific calculus concept that is known as the derivative. So, let's say you were going on a road trip, and you drove for 1 hour, and while you were driving, you drove 70 miles. How fast did you go? Well, we can think about this as a graph, actually. So we went 70 miles and we drove for 60 minutes or 1 hour. And at some points we were going maybe a little bit slower, and at other points we were going a little bit faster. Our average speed is 70 miles an hour, which gives the slope of this blue line here. How could we find our speed at just one moment in time, though? It's the same idea as the slope, but we need to look at just a very small section. So if we zoom in on this little point, we can see that we still have a slope of a line, but it's just a lot smaller. So now we're going to get a little bit mathematical. The slope of this line is equal to the rise over the run. We first need to look at the rise, or how much it's going up. It'll be the same idea of what we just did, so we'll have our ending point, just like how we ended at 70 miles, at f of x plus t, where f of x is what we're going to call our function, and t is how long we traveled. And then we'll subtract that from our beginning, which we will just call f of x. So that's our end minus our start, and then on the bottom we just have t, which is how long it took us to go across. So that gives us our full slope equation, which is f of x plus t minus f of x over t. In order to get this down to just 1 point, we need to make t really, really small, because we don't want any kind of a slope at all. We want to just look at one spot. So we don't want to be going over it all. How can we make something that small? Well, we need to take the limits. But what is the limit? Well, the limit helps us predict what the function will be like at just 1 point. So one way to do that is we can look at how the function acts as it gets closer and closer to that point. Let's take the example x squared. At x equals 1, x squared equals 1. At x equals 1/2, x squared equals 0.25. And you can see where this is going. As we get closer and closer to 0, as x gets closer and closer to 0, x squared also gets closer and closer to 0. So if we take the limit as x approaches 0, or gets closer and closer to 0, then we can say that x squared equals 0. Now, let's try applying that same idea to our original function. We need to look at how the function is behaving as we get closer and closer to our point. We can predict what it'll be at that point. Now that we have that, we can take the limit of our slope function and get the slope at just 1 point. Finding this slope is what gives us the derivative. Now that we know what the derivative is, let's look at the anatomy of the derivative. There's two main forms. You have what looks like a fraction, where you have d over d something, in our case it was t, times the function of a variable. Or you can just have your function, f of t, and then put a little prime sign right there. So then we'd say we have f prime of t. Okay, there are three main symbolic forms, or ways of thinking about what the derivative is. The first is the slope of the line at any point on a function. The second, which is related to the first, is the instant speed. And an example of this in real life is actually your speedometer in your car. It gives you the instant speed, or the speed that you are currently at any one point. And the third is the opposite of the integral. So just like how multiplication and division are opposites of each other, you can do multiplication and then you can do division to reverse it. You can do integration and derivatives to their opposites of each other. They reverse each other. So those are three symbolic forms of what the derivative is. I'm glad you joined me in learning about the derivative, how to find it, what it means, and 3 different symbolic forms of it. I hope you learned something new and you feel smarter, and thank you so much for joining me.